Hi everyone! This video is for students who are finishing up their first year of general chemistry and will be moving on to Organic Chemistry 1 starting either this summer or later on in the fall. All of these topics were topics that I specifically went over myself as a Gen Chem to OChem student last year, and these are topics that were also referred by organic chemistry teachers and students of the past. The first topic to go over are all of the periodic properties that y'all went through in all of general chemistry. The primary ones to know are shown here in the video here, and they're demonstrated with all of these colorful arrows right here with this periodic table. The reason why it's important, I'll get there in a little bit. I'm going to scroll on down as to why it's important. Why do you have to know all of this? Well, essentially in organic chemistry, you'll be going over a mix of how all of these merge together and how these organic elements, in particular, the ones here in the, I'll highlight it here in red, in the reactive nonmetals, aka the organic metals. You work primarily in a lot of these elements, a lot in carbon, a lot in nitrogen, oxygen, a lot of the halogens here, these four primarily. Sometimes you work in sulfur, sometimes phosphorus, hydrogen a lot, and yeah, essentially knowing all of your periodic properties, specifically the big ones I would highlight in particular would be electronegativity, ionization energy, and atomic radius, and the direction where they go. So electronegativity goes from left to right, and electronegativity increases from bottom to top. So all of the arrows here are in the direction of increasing. So all of these are in the direction of increasing. Because for me and my brain, it makes the most sense to have everything increasing rather than going increasing then decreasing. It makes my life easier for me. All of these are important because they explain the basis of what you go through in OChem 1, which is why these organic molecules react in a certain way, why they behave a certain way, why some have electrons that move from one element to another, why certain anions are very rich in electrons, why metals are used as catalysts in organic reactions, why nonmetals are primarily used in organic chemistry. And the two ones that I've highlighted in yellow here are to understand these concepts that you'll get to understand better in OChem 1, which is electrophiles, nucleophiles, and inductive effect, which is why I've highlighted, or starred actually, these three boxes to really focus on the most, but do not avoid looking over the other three boxes as well, with reactivity of metals and nonmetals and electron affinity. Essentially, this explains in OChem what is electron rich and what is electron poor. You'll be hearing that a lot in Organic Chemistry 1. And what that means is, what is a molecule who has a lot of electrons, so a lot of the lone pairs, or those who do not have a lot of lone pairs or electrons. The next thing you want to review from Gen Chem as you move on to OChem are Lewis structures. This is probably way in the beginning of Gen Chem, like 1, but it's a big part of what makes OChem. OChem is you draw a lot. The Lewis structures, what's important about them is you want to understand what a sigma line and a pi line are, or a sigma bond and a pi bond. A sigma bond is just a single line, and two bonds like this, the double bond is a sigma. So sigma is in this symbol and pi is in this symbol. What's important about Lewis structures is that they are visualizing the organic molecules to explain their reactivity, aka, again, electron rich versus electron poor. They also help predict the shapes This is a concept that is kind of emphasized a lot in biology, but structure function, the structure is going to beget the function of how these molecules work. In particular, I'm going over here, you're used to seeing maybe the dot structure with the full Lewis. The full Lewis here. The half Lewis is what you're probably most used to, where you write out each element and you have your single line here, single line indicating your single bond or your sigma bond, and then the dots indicating the lone pairs. But in OChem, and you can see here and highlight it in yellow, the rule 1 of organic chemistry is that chemists are lazy, which means that in OChem, we like to not emphasize like all the carbons and all the hydrogens a lot. So we use a shorthand version called line angle formula, where all the carbons and hydrogens are now going to be invisible while the other elements are shown. There's other versions, I'm going to zoom on in here, of how we use this formula. There is this kind of formula, which is what you're used to in Gen Chem. And then this right here is known as a condensed formula. You'll go more in depth about it in OChem, but I wanted to show you what this looks like. And the reason why we have the condensed formula, I'll show you an example later, but it gives a blueprint to the organic chemist looking at it, what exactly is the potential shape of this molecule. Because if you only had this, that's not enough information. This gives a little bit more information. Yes, it's a lot of words and they look maybe kind of scary, but now that I've been in OChem for a year, I really prefer seeing this one versus the one on the left. So here's an example. This is the structure that you're used to seeing. This is the full Lewis. Well, full Lewis / half. Half is actually more accurate, the half Lewis. This is even more condensed. So instead of me writing out all of the CH3s, I just wrote out CH3, and I wrote it backwards because all of these hydrogens are out here. So I just condensed it into saying there's 3 H's. And the carbon here is what's actually connecting to this carbon, right? And instead of putting the lone pairs with the oxygen, I don't have them there. I just know intrinsically that they're there. So the O and the H come together. I indicate that there's like a lone H at the bottom here, and I have another CH3. Cool. So that's condensed. We can go even further, as you can see right over here, and go way, 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 way deeper. So you can see, and I'll erase this on the side, less chaotic. So you can see how these stayed the same, and this stayed the same, but I changed the orientation. And the reason why is because shape matters a lot in OChem. This is about, if you remember your Vesper theory, which we will get back to in a little bit. I was kind of hinting towards it right here. Molecular geometry, we'll get there in a little bit. It tells you about the repulsion that is occurring between these atoms and molecules as it creates its shape. And then I can go even further and I'm going to get rid of the H's completely. That's a little scary, right? But I know intrinsically that they're there. My big advice is when you're first starting out and you're not used to the line angle formula, which I'm about to show, draw out the H's, draw out the CH3s, draw out the C's, so you know where you are until you've done enough practice where this becomes second nature. So now this is the entire formula at the very end. This is the line angle structure. We went all the way from here at the very beginning all the way to here at the very end. See how the one at the very end is so much faster than the one on the far left? Yep. That makes it so much easier in OChem versus the one on the far left. Okay. Here's a little bit of some practice problems here. You can pause this video right now and try these out for yourself. And I will go through the answers. So feel free to pause the video right now and give it a try. Okay, I'm going to zoom on in and start with the first question here. So That is one long string of words, okay? When I first looked at this when I was in OChem 1, I was like, I don't even know where to start. So if it helps to start doing what you know, which is like, I need to draw out every carbon, every hydrogen, then do that. Start there so you can at least see what it's supposed to be. But see how that takes forever? It's okay. You're starting out. You have your O and a CH. Oh, see, automatically my brain wants to condense because I've done this well, and that's okay. You will too. So this is a valid structure, but it's not what I'm looking for. My goal for this is for you to practice line angle structure. So another way you can do it is you can start here. The next thing you can do is try the condensed version. Well, how about I do CH3? And it's okay if you write the CH3 like this to start until you get used to writing it, backwards like this. But I'm pretending I'm back in OChem 3, or OChem 1, sorry. So I start with the CH3, and then I say, okay, now I'm at CH2, and I'm at CH2, and then I have an O, and I know I have lone pairs there, but I'm not going to draw them, and a CH3. Very valid. Absolutely valid. Now what you want to do is start getting into the habit of completely avoiding going, these steps, but, I was here in your steps, in your feet, and in your shoes, and this is how I started, and now what I can do is I can start figuring out, okay, this right here is a CH3. Intrinsically, I know it's there. That's a CH2. That's a CH2. And that CH2 is connected to this O. And again, I know there's lone pairs there. And that is the CH3. So at the very end, and I'm just going to highlight here, even though I have not marked the hydrogens, they are there. They live there. They exist there. Okay? You just have to get used to this. Totally fine. If your structure did not come out this way, that's totally fine because you could draw it, and I'll erase this up top. You could draw it this way as well. You could start CH3, CH2, CH2, oxygen, CH3. Both are valid. Both are the correct answer. Okay? So we'll move on to number 2. That seems a little bit more intimidating, but I swear it's not. So I'm immediately going to go into the line angle structure just to kind of save on some time. So I know that I have 2 CH3s. So that means I'm going to have one line maybe somewhere around here. I'm going to have another line, somewhere around here. And I know that I have this C that is going to a CH and a CH2. And it says that there's a double bond. All right. So that tells me that I have these 2 methyls. Well, methyls is the shorthand, if that kind of helps. Methyl is the shorthand for a CH3. I have these 2 methyls, and I'm going to create my double bond here because this C is connected to this double bond. Then I have, if it helps to draw the hydrogen, please do. So then you have this carbon here that is attached to a hydrogen, and that is then attached to a CH2, and then also attached to a CH3. So if it helps to draw the hydrogen, please do. Otherwise, you don't have to draw it, and it will look like something like this. Totally welcome to finagle it. The more proper way to draw it would be something like this. Okay? And if it doesn't look like that, it's more like flipped upside down, that's totally a valid answer as well. Last one, CH3CHO. I've kind of, when I was in the beginning, go like, I don't even know where to start. Like, there's an oxygen, there's a carbon, I don't know. Even though it doesn't say that there's a double bond, you'll eventually get used to understanding that this suffix in a condensed formula is the symbol for an aldehyde. And you'll understand what an aldehyde is in OChem, but it is a type of functional group. So this one was a little bit of a tricky one. Apologies. So I know I have a CH3. I am going to have a C double bonded O. And it's up to you if you would like to mark the H or not. I tend to, with aldehydes, always mark my H's. Otherwise, I will totally forget that it exists. Very valid. And those are the answers for those three. Excellent. The next thing that aligns with understanding and remembering your Lewis structures is remembering formal charge. So there's two ways that you can go about with formal charge. There is the formula that we're used to from Gen Chem, valence electron number minus, the lone pairs, LP stands for lone pair, E negative plus the half bound E. I go with my little thing that I got from Leia for Science, which is I do should minus has. It is the number of valence electrons the atom should have minus the number of electrons the atom has directly attached to the atom in question. So feel free to pause the video here, use whichever one I've said here that you like best, and come back when you are ready. Okay, back, and we'll start with the nitrogen. Nitrogen is, I feel like, one of the easier ones. So nitrogen, it should have about 5 valence electrons. And you know that, and if you don't remember, I'll just go back a little quick to the periodic table here. Remember that this is 1, 2, and I'll erase all of this. 3, 4, 5, 6, 7, 8. So these are the valence electrons. I'm not talking about charges, valence electrons. So nitrogen is in the column where 5 is, so that means it should have 5 valence electrons. Oh, apologies, I just skipped way too forward. Sorry. It should have 5 valence electrons, but it doesn't, right? And so I am going to count here how much I have, which is like, all right, what is surrounding the nitrogen? I have 1, 2, 3, 4. And the reason why I'm counting 4 is not just because it's the lines. It's not just the lines. It's because if I was to slice this single bond over here in half, 1 dot is here and 1 dot is here. Okay? So 1, 2, 3, 4, it's going to have 4, and then that equals a positive 1. So this nitrogen here is going to have a plus charge right next to it. We'll do the oxygen next, that is labeled in green. So oxygen should have a valence electrons of 6. Now, what I tend to do is either put a box around the element and then count, from there, or I just count every dot and every line in the structure. So 1, 2, 3, 4, 5, 6. It has 6, so therefore it has a neutral charge. Fantastic. Last one, in purple. These are both the same, so whichever one you do is going to be the same for the other. Oxygen, again, is supposed to have 6 electrons. How many does it technically have? It has 1, 2, 3, 4, 5, 6, 7. And that comes out with a negative charge of 1, which means that this oxygen over here needs to have a negative charge, and this one over here has to have a negative charge. And the reason why it's important to remember your formal charges is because you will be doing a lot of pluses and minuses in OChem, as in where did my electrons go, where did my hydrogens go, and if it took away something from an element, that means it's probably changed its formal charge, which means it's probably either electron rich, so negative charge, or electron poor, which is a positive charge. And hopefully that kind of made sense. Next one to go over is hybridization, molecular orbital theory. Feel free to pause this video at any point while I'm talking. I don't want to go too in depth about this because it can get pretty confusing. I needed to highlight this though because it's super important in organic chemistry. We tend to use the hybrid orbitals of sp3, sp2, and sp. It is very rare to use sp3d in organic chemistry. I can't even remember a time, honestly, in the whole year that we've ever used sp3d. So majority of the time it's sp3, sp2, sp. Molecular orbital theory exists, and why it's important for OChem is because it's going to explain the bonding and properties of these organic molecules when they're combining your s orbitals and your p orbitals together. So you can see in this little graph over here, this is what it's traditionally supposed to look like for a ground state carbon. You have these two arrows here, fill the valence electron shell, which means it's not available for bonding. That's the 1s orbital. The 2s orbital is full. But if you notice here at ground state, there's a whole empty box here. Okay? Now what happens is that once it becomes excited, which I didn't draw here, but that's neither here nor there, you worry about that later. When it becomes excited, which means it's gotten some energy and it's changed, again, structure, function, change shape, hybridization then occurs when you mix one s orbital with three p orbitals together, as it shows here, and you basically have distributed those half arrows into separate boxes. Again, I don't want to go too in depth. And again, you can pause this video whenever you would like to kind of like really read what's on here. I just know that I needed to have you keep this in mind for organic chemistry. Like I said, we use this a lot, in particular with things called conjugated system, aromatic compounds, a lot of things that are highlighted in yellow in this video. Super important in understanding reaction intermediates, resonance structures, delocalized electrons and whatnot. So that means that you have a condensed Vesper table, which is pretty awesome. In OChem 1, I had to kind of try and learn to memorize these, but memorization was not enough for OChem, and I didn't have a Vesper table on the exam, so I had to really understand why and when a molecule has a certain hybridization. Like, why is it sp3 for its hybridization, but its molecular shape is going to be, trigonal, pyramidal, or bent? And it's because of the lone pairs changing the angle of the geometry as you do that. A rule that I used in OChem, as it shows right here, is something that I got from a book I'll reference later. It was super helpful. So when you add up your lines and you add up, mainly not lines, you add up your sigma bonds and your lone pairs, not as individual like I did with the formal charge, but as in a pair together, like here in sp2. Here's 1, here's 2, here's 3. I am not counting this pi bond. Don't count the pi bonds. So add all the sigma bonds, add each lone pair, and that will tell you its hybridization. And that gets you halfway to understanding what is its molecular geometry. It was super helpful as I was in OChem. This is a huge molecule. I do not expect you to do every single part of this molecule and count out what is the hybridization and geometry of every single molecule. If you want to, go for it. I am only going to be circling the areas that I want you to practice. So I want you to practice here, and here, and here, and here, and for the sake of it, let's do this one here. Okay, pause the video and go ahead and try figuring out what is the hybridization of these 5 points on this gigantic molecule. Okay, right, we are back. So let's start with, in my opinion, is a little bit of the easier one. So it helps when you're first starting out to write out what is on there. So this is a C, and it's got a bunch of H's around it. And then you count the sigma bonds. So 1, 2, 3, 4. That means this part here is a hybridization of sp3. Hopefully that one made a little bit of sense. This one over here on the far left, might be a tiny bit harder. So it's super helpful to draw out the missing hydrogen. And this right here is a carbon. So this carbon has 1 sigma bond, 2 sigma bonds, 3 sigma bonds. And again, we don't count that pi bond. So 1, 2, 3, this has a hybridization of sp2. Which means that this one over here also has a hybridization of sp2. Now the ones that's in the triple bonds are a little bit tougher, because you're like, is there a carbon here on the far right and the far left? There is. They're hidden. So for triple bonds, what I got into the habit of doing until I got used to it is I drew out a C and I drew out a C here, and then I would add an H at the end to remind myself there's actually 2 carbons here. I'm not going to make a mistake and forget that they actually have, hidden carbons. Okay? So with this one right here, you have 1 sigma bond, 2 sigma bonds. We do not count these right here. And that means that this has sp hybridization. And it's going to be the same over here with this carbon. It has 1 sigma bond, 2 sigma bonds. 2 equals sp3, 3 equals sp2, 4 equals sp3. Cool. Now, this one, practicing drawing geometry, okay? These might be a little bit tough, and there's not going to be a wrong answer with any of these, and I'll explain why after you pause the video and give it a whirl. Try drawing these molecules. Okay, we're back. So, with the first one, this is a mouthful of a name. This is bromochlorofluoromethane, if I'm remembering correctly. And essentially how you could have drawn it is one way, which is just Br connected to a carbon, to an H, to a Cl, and to an F. That's totally valid. And then ask yourself, what kind of hybridization is this? This is going to be an sp3 hybridization. There's no lone pairs, so it's just tetrahedral electron geometry and tetrahedral molecular geometry. There is a thing that we use a lot in OChem, and that's why I wanted to use this one as the first example. And that is called wedges and dashes. So a wedge looks like this, like a triangle, and a dash looks like this. A wedge means that if I had a piece of paper in front of me, that means that the molecule is coming towards me, and the dashes mean that the molecule is going away from me. Now, when I was in OChem, none of that made sense, a lick of sense. So what I tried to also try and make in my head is like, so a wedge means that something is coming not towards me, but it's at the front of a molecule, while the dash means it's going behind the molecule. And the molecule in question is the carbon itself. So the wedge would mean that whatever molecule is on the wedge, it's going in front of that carbon, and whatever molecule is on the dash is going to go behind the carbon, which you're like, oh, now that makes more sense. And hopefully it did to you as well. This means that because this is sp3 geometry tends to use wedges and dashes a lot. And that's why I said nothing's really going to be wrong from here if you want to just pick who's going to be on a wedge, who's going to be on a dash. You'll go in more in OChem as to how it, should be or potentially could be, like who would be on a wedge, who would be on a dash, and how sometimes it will change because you rotate the molecule. Again, that's not something you need to focus on right now. So what I drew for my answer is I put chlorine down here, bromine down here. I did not draw out the actual carbon itself because it's intrinsically, I know it's right here what the dot is. I put the fluorine on the dash, and I put the hydrogen, and I did mark it here, the hydrogen on a wedge. And the reason why I marked it is because if I did not mark here, I'm intrinsically going to guess that this is going to be a CH3, which would be incorrect, okay? So sometimes it is good to actually mark out your hydrogen, okay? And so that's a valid answer. You could obviously change it around. The bromine could be on the wedge, the fluorine could be on the dash, or even this one. Both are valid. But I wanted to bring that to your attention that with sp3 molecules, you'll see them a lot more with wedges and dashes going forward with OChem. And that's what wedges and dashes mean. Because we didn't really talk about them in Gen Chem. This one might have been a little confusing because you're like, wow, there's 2 oxygens. Maybe they're like, maybe one's up there, maybe one's down there of the carbon. So the answer is I have a CH3. So the CH3 is right here. It's intrinsically, I know it's there. I know that there's going to be a carbon right here, but I'm not going to draw it. I know that this is going to be a double bonded O, and that it's going to have an OH right over here. And again, the reason why I know that, and you will learn it later, is this is a code to know what a functional group known as carboxylic acid. COOH is the symbol for carboxylic acid, but did not expect you to know that at this stage. This one was really hard, and that's why I gave you the hint. It's also a good demonstration of why in OChem we don't use that anymore. That's not enough information. This was way more information to give you at least some sort of guidance as to how to draw a potential molecule, because you know that you have 2 methyls, you have 2 methyls, so you have 4 methyls, and you have a C and an H and a C and an H. That gives you a vague idea of how to draw this. So the answer is that, because again, this is a hard one, CH3, so there's CH3 right up here, and there's going to be a CH3 right over here, right? I'm actually going to get rid of the dots, okay? And then there is a hidden, you can even put this on a dash if you want, totally fine. There's a hidden hydrogen, and there's a carbon here, and that equals an octet, right? So 1, 2, 3, 4, perfect. That carbon that's hidden there is very happy. And now you have it attached to another CH, so you have a CH. And again, if you want to put the hidden hydrogen here on a dash or a wedge, I don't care, you're welcome to. And then you have another CH3 and another CH3. And that's the answer. Little tricky, but this is why you're practicing. Moving on to the next topic. And to me, this is a good chunk of organic chemistry, is acid-base chemistry. The questions that you will be asking yourself a lot in OChem is, who's my acid? Not who's my acid, who's my base? You're going to be asking who of the molecules is donating, who is accepting? Where do my protons go? Where do the electrons go? What is going to make a proton, aka a hydrogen, more acidic or basic than other hydrogens inside of a structure? And the 2 concepts that you really want to drill into your head before you go into OChem, I would consider this, out of everything, the most important aspect to get your mind around before you walk into the first day of OChem, is reviewing this material on Bronsted-Lowry acids and Lewis acids and bases, okay? Which I believe in Gen Chem we did not go over, so I'm going over it with you right now. So Bronsted-Lowry acids and bases is something that should be a little bit familiar to you. The acids are donating the protons and the bases are accepting the protons. Lewis acids and bases are similar, except if you're noticing a difference here, this is all about electron pair, aka, if it's easier to wrap your brain around it, it's called lone pairs. You can even call them pi electrons, because those electrons tend to also make the pi bonds. And they just kind of go back and forth, and kind of making bonds. I recommend just putting your brain around these being called electron pair or lone pairs versus thinking about anything else. So the Lewis acids will be accepting the electrons while bases will be donating the electrons. So here's a classic example of a Bronsted-Lowry acid base. So we have HF plus ammonia turns into ammonium and the fluoride ion. What I'm going to demonstrate now is a classic demonstration of what is called tail to head arrow, which I believe was referenced to in lab, but now I'm going to actually demonstrate another fundamental bit of OChem, which is we draw arrows a lot because, again, the key question is, where did the protons go? Where did my electrons go? Who's donating and who is accepting? Super important. So, how did we end up getting this conjugate base and this conjugate acid over here? Well, yes, a proton was taken away and it was added to this hydrogen, or this nitrogen, excuse me, right? But now I'm going to demonstrate how that happened. These lone pairs on this ammonia, which is an sp3, but it has a lone pair, so it's not tetrahedral, it's trigonal planar. It's coming over here, and it is going to be taking this hydrogen away. When the hydrogen is taken away, this poor little bond has to go somewhere, so it's going to go here to the fluorine, and it's going to become that lone pair over here, while this hydrogen got attached over here. And that is why this nitrogen now has a plus charge, intrinsically a +1, and this fluorine is now an ion because it had electrons added to it. This is electron rich, and this is electron poor. Which means that, yes, this is a Bronsted-Lowry acid, this is a Bronsted-Lowry base, but this is also going to be a Lewis acid and a Lewis base. Because not only were protons donated and accepted, electrons were donated and accepted as well in order to create these new bonds and new molecules. So this is very similar. This is both Bronsted-Lowry and Lewis acid. It worked here, and I'm going to show it again, where one of these electrons got donated, and yes, you can see who donated and who accepted, but I'm going to show it with the arrow. What happened is that these electrons here went over and said, howdy doody, how you doing? Taking you, Mr. Hydrogen, stealing you away. And then that poor bond needs help, so it's going to come in and it's going to attach itself to the oxygen over here on this, this NO3. Okay, so now you're like, oh, where did that bond go? It went right here, or you can even say it's right up here, which has a negative charge, and this oxygen has a positive charge because those lone pairs became a bond to the hydrogen. Very good. That doesn't mean, so key thing to also wrap your mind around, that doesn't mean that every Lewis acid base is going to be Bronsted-Lowry acid base. And that's where we come to our last example, a classic example of Lewis acid and base. So over here on your very left is BF3, and BF3 is what's the name of it? Boron trifluoride. I should have known that. Boron trifluoride, and then the one on the right is going to be your ammonia. So you're like, but it's not making a molecule. It's not making two separate molecules. No, it's not. These electrons here from this nitrogen came on in and attacked this boron. And why it attacked this boron and therefore created this bond here is because this ammonia was more electron rich here because it has this lone pair, while boron, because if you remember from way in the beginning of Gen Chem 1, boron is super happy just being at like an octet, not an octet, but just being at 6, which is what we have here. 1, 2, 3, 4, 5, 6, right? But if you do that, it's like, now I'm going to have extra electrons, so I'm not going to be super happy, but I'll exist. And that's why it's got a negative charge. Meanwhile, nitrogen's lost its lone pairs. It's saying, boo, I miss it. And now it's got a positive charge. This is known as a Lewis acid-base complex. And I wanted to bring this one up because it's a classic example of how a Lewis acid and a Lewis base will not be Bronsted-Laurier at all because of what it's creating. Now, I wanted to bring up this key point. Remember this as a guiding light in organic chemistry. Follow your electrons and see who donates and see who accepts. The ones who accept are the ones who need help because they, again, are electron deficient. They are electron poor. The ones who are donating are very electron rich and they have things to give up. Okay? So, we're just going to do one last practice problem before wrapping up this extremely long video. Pause here and try out those arrows. So a mechanism is the arrows here where you have your tail and you have your head. Draw out on here, or draw this out on a piece of paper and show me how is this getting formed over here. Who took what from where? Who donated? Who accepted? And is this Lewis acid base? Okay, we're back. When I was first in OChem, I drew everything out. I was not used to things being in shorthand like this, was not used to not seeing some lone pairs. So, you darn tootin', I put down the lone pairs around an oxygen. I put some lone pairs around that oxygen, and it's a little tiny, but I'm going to put a bond right there indicating that I have a bond between the oxygen and the hydrogen. Okay? I'm going to circle one of these lone pairs. You don't have to. It's just something that I did. And I'm going to bring the arrow over here saying, I'm picking up this hydrogen. What's up? How you doing? That means that this tiny little bond has to go over here and it becomes best friends with the oxygen. And that's why this oxygen is electron rich, has 3 sets of lone pairs. And you could call this one electron poor, but maybe not. It's just creating what's called methanol. And you can create a little bond here, and you can create a little bond here. And this has lone pairs around that oxygen. And there you go. Cool. That means that that negative charge has now become neutral. And that was your last problem. You did it. You made it to the end of the video. Woohoo! Okay. Last page is all about the resources and tips I am going to be giving all of you to hopefully succeed in OChem, because I will say that after taking organic chemistry for a whole year and currently studying for the ACS organic chemistry exam, which is the final, I have to do a 70 question exam, which goes over the entire year of organic chemistry concepts. And yeah, it's the entire year of content from OChems 1, 2, and 3. This is what I did and utilized to succeed the best I can in OChem. I do believe everybody can get an A, or, you know, whatever you would like to get in this class. It's very, it can be very trying, I will say. It can be very trying. But you could definitely do it. So the number one thing I would recommend for everybody is get your hands on OChem as a second language book. So the ones that I have done in like bold and italicized are the ones that I highly, highly, highly recommend. This is the, let's see, this is the 5th edition right here, and this is the 4th edition. I was given the 4th edition and it was fine for first term, and then I ended up buying the second term 5th edition. It's kind of cost prohibitive, so if you can get your hands on the 4th, which I believe is a little bit cheaper, do so. And yeah, that's definitely my favorite thing that I did for OChem 1 and for 2 a little bit. YouTube is a great resource as well. these are all of the channels that I watched. The one that I recommend the most is Professor Iman. She is amazing. For those who are pre-med who are watching this video, she does a bunch of pre-med videos for the MCAT, which I've been utilizing as I study for the MCAT as well. I love it, and I love her, and the way that she breaks down the material for organic chemistry is extremely accessible to me. So hopefully it's accessible to you. Highly recommend for OChem 1 that you also get a model kit. The one that is bolded and italicized, which is this one right here. That's the one that I used. That's the one that I used throughout all of OChem 1. Didn't really use it that much in 2. Didn't use it at all in 3. But for those who are going into OChem 1, please get a model kit. Please, 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 please. Both the Old Nobby and Duluth labs are not too cost prohibitive. You can get them for, I believe, about less than $25 or about $25. I can't remember how much it costs. But yeah, highly recommend getting a model kit so that you can actually see the molecules that we did today in real time and actually get to play with them. Khan Academy, love it. Cannot recommend it enough. Super helpful resources, and it's just great to hear the material in, like it says, great to hear the material in a different way than what you see in class. This is everything I did to, well, I'm actually going to cross this out and say succeed. Survive OChem is actually more accurate. I can read, I can't even speak anymore. I can dictate what it says here on this video. The ones that I would put a star next to as like I really recommend it to everybody as things that I did that I encourage everybody else to do is, or at least try it. And if you don't like it, that's okay. Is this. I used it on my exams when I have an issue of getting really, really annoyed when I can't draw a perfect hexagon or a pentagon. Pentagons have now become the bane of my existence. Hexagons became easier. So this stencil was perfect. The exam edition does not have any notations whatsoever that you can utilize it on your exams for OChem, and I had no issue using it. I also highly recommend doing the OChem workshop. I did it for second and third term. I wish I had done it for first term. There are a lot of practice problems that you get to use, and they are a little bit more difficult than the ones that are actually on the exam, so highly recommend that. I even attended office hours as much as I can every week with the professor, even if I had no questions. Just being there and practicing or like reading through the material and reviewing the stuff that we just did in class, or even redoing my notes because I scribble a lot like a silly person, making sure like I can catch up with whatever was drawn or said about. It was super helpful doing that. I used the Learning Center OChem tutors a lot. They were my saviors so much. I cannot emphasize that enough. Obviously, the OChem as a second language book, highly recommend that. I did YouTube in the end more so than Khan Academy. In the beginning, I used both, but once I kind of figured out how I best learn OChem, YouTube, especially Professor Iman, end up being my go-to person. Anki, you can do Anki, Sketchy, study groups are for me like super important because that's how I like to best learn, is how just to teach and work with others and talk things out and hear other people talk about how they are learning OChem and how they come up with their own way of understanding material. As you can tell, I did have a rubber duck dressed like a mad scientist that I would talk to while I'm at home alone. Another thing that I used to do and are still doing on the exams in particular is I would do what's called an info dump. But what that means is that I'm not like creating a cheat sheet per se. It's more of, for an example, I am consistently messing up something called enantiomers and diastereomers every single time. Or every single time I see Markovnikov and anti-Markovnikov, I am forgetting which one is which. Does it go on the more subside or on the left subside? And so I write that down immediately when I get my exam so I don't forget it. So then I can just tell my brain, hey, if you see that, don't forget, it's right there. It's my little like handy dandy helper to help me through exams. Because for OChem 1, I had no cheat sheet. There's no cheat sheet in OChem 1 like there is for Gen Chem the entire year. Who knows? Maybe you'll have one this fall. I don't know. But for us, nope, we didn't have one. The most effective way, in my opinion, of how I have succeeded in OChem is practicing. Practice, 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 practice. And it doesn't mean you practice for hours on end. No, no, no. Practice 5 or 6 days a week, 25 minutes minimum. Do not go beyond 1.5 hours. I think that's just overkill. And give yourself breaks. Some weeks you might only do like, 1 to 2 days because you're going to have other classes. This is not the only class you're going to do. But I will say what has helped is at least carving out once a day, 25 minutes. And sometimes I couldn't even do 25. Sometimes I would just do 10 minutes, better than nothing. Or, 12 minutes, better than nothing. Or 15 minutes, better than nothing. I would strive to get to 25. But if I couldn't, it's not the end of the world. So 10 minutes, 12 minutes, 5 minutes. If it was a really bad day and I'm exhausted, I'm like, all right, I can just do 5 minutes. I can do 5 minutes. I can do one practice problem, PP for practice problem. That's something rather than nothing. So try and make a habit out of it. Hopefully everything I've mentioned here seems a little helpful. Hopefully this entire video has been super helpful. And thank you so much for watching. If you have any questions, you can leave them in the comments below. And good luck to everyone who's going to go on to Organic Chemistry 1. Firmly believe that all of you can do amazing in this class. And just so you know, if everything that I've said towards the end of this video about resources and tips has not helped you at all, please go to the academic coaches. Please talk to the STEM academic coaches as well, particularly Katie and Alyssa. They are amazing. I use them myself. And hopefully that is helpful for you. And yeah, that is about it. Thank you so much again for watching. And you've got this. You are awesome. You are fantastic. You are great. You are stupendous. And you are going to conquer organic chemistry to the best of your ability.